Radioactive decay. I'm going to load calculator stuff here. Okay. Let's go back to the screen. Alright. So get your data into the calculator, and you can see that the let's just look at it. So here's the stuff in the calculator. Let me get rid of the things in L3. Okay. Let's just do a scatter plot on L1 and L2 to make sure we're all squared away, that we can see that it is curved, that we do not have a straight association. Zoom 9. Okay, so without even looking at the residuals, that was my line of regression. Let me get rid of that. Okay. Without even looking at the residuals, we know that we have to straighten this line out. So let's try, since it's all the numbers are positive, okay, all the y values are positive, and we have a curved exponential looking, like exponential decay. I mean, this is exponential decay. That's what radioactive decay is. It decays over a certain period of time. It has a half-life and all of that. Anyway, with a fixed percentage. Since it's exponential, we'll try the log, since the log is the inverse operation for the exponent. So we'll go to Stat, and we'll edit, and we'll go to L3, go to the top, and we'll hit log second 2. Hit enter. Now we got the logs. And again, just to make sure we did this right, I'm going to put in 10, up arrow L3. So in other words, I'm going to take the numbers that I generated in L3, and I'm going to raise 10 to that power, and I get L2 back. So I know that I really have the logs of L2 in L3. So I'm going to clear L4 out because I'm not going to be using it. Now I'm going to do a scatter plot on L1 and L3. And do a zoom 9, and that looks really straight. And you can see, because now the y coordinates are logarithms, that is, they're these numbers here, that the rate of change is much smaller. Okay, much more gradual. There's not a steady rate of change between as you go down L2. Okay, here it goes down almost 100, down here. So between 0 and 2 it goes down almost 100. Between 8 and 10 it only goes down about 13. So you don't have a constant rate of change, which is what makes something linear. On the other hand, this looks more, it's not completely linear, but the rate of change looks much less drastic than it is in this column here. And why? Because this is the exponent that you raise 10 to in order to get this number. So exponents are going to change at a much slower rate than the actual number that is the product of 10 raised to this power. Okay, so that's why logs work often so well in straightening out a curved scatter plot. Okay, so we got, this looks promising, so we're going to go ahead and run the regression. Now let's make sure that diagnostic is turned on. I hit second and 0. I hit the inverse key to put me in the D's. I go down 9. I hit enter, enter again. Okay, so I'm going to clear the screen. And I'm going to do stat calc 8 on L1 and L3. Okay, okay, a plus bx, hit enter. All right, that's the numbers that I have on the screen here. So now I ran this so I can check the residuals. So I do second and y equals and enter. Okay, and I enter down to y, go down to y list and hit second and stat 7 for res ID, enter, and zoom 9. Okay. All right, it's not great, but the thing is there's only 6 points. So unless the points are arranged in a completely parabolic curve like this, then I gotta say this is about as, consider I only got 6 points, this is fairly random looking. I got 2 above and 4 below, one's right on the line, 3 below. Anyway, it could be worse. It would certainly be worse with this line. The residuals with this line would definitely look like a parabola. Okay, they would be completely curved. Okay, so this is not, so we're going to go with this. So what's going to be our, let's see, now this is, I got to retype this. This is the log. All right, and it's the log of the estimated element in grams. Okay. All right, equals, okay, so control F4. Okay. So that's the equation. 2.5 minus 0.0749 times days. All right, so what's the predicted amount of the element after 30 minutes? Well, there's a couple, that's, in other words, half an hour, or 1/48th of a day. Okay, so what's the different ways we can do this? Well, we could take the equation and plug in 1/48. So let's do that. So we'll take 2.5 minus 0.0749 times 1 divided by 48. In other words, half an hour. Okay, now we get an exponent here. And we'll raise 10 to this power. And so we got 315 grams. Now notice this is different than my answer here. And the reason is that because of rounding, maybe I put in the wrong number. Let's see. Yeah, it's 2.505. So let me, if I put 2.505, then I would have come up with 318, because it makes a little bit of difference. Here's the thing. This is one of the reasons why when I'm working with re-expression, I don't want to use the sort of the rounded off decimals and all of that in order to come up with my answers, because a tiny little difference in an exponent makes a big difference in the answer. 318 is pretty different than 315. So this is why I prefer to do this, especially when working with re-expression. I want to turn this plot. Let me turn the plot back to L1 and L3. This will just help with my. Okay. Now I'm going to go to second and y equals. I'm sorry, y equals, and I'm going to put in the equation with all the decimal places. The more decimal places, the better when you're working with re-expression, because then your answers will be much more accurate. Now, if you weren't working with re-expression, if you weren't turning things into logs or square roots or whatever, it wouldn't matter as much. But when you're going to take a log and apply it, make it the exponent of the base to produce the real amount, you want that log to be as accurate as possible. So I'm going to go to vars and 5 for statistics and arrow over to EQ, And so there's the equation with all the decimal places. No rounding, as many as the calculator can produce. And then in y2, I will put 10 raised to the power of y1. So I go back to vars. Now I'm going to go to y-vars because that's where the variables are under function. Okay, y1. Okay, so now I wanted to know what it is for half a day. So if I go to second and window and table set, I go to the independent. That's that's the x variable, and I turn on ask. Then I can go and let's see where we start now. We're starting at 1. That's good. Okay. And second and table. Second and table. I had graph. I don't want graph. It's doing its thing. Okay. Okay. So x equals 0.5. I'm putting in half an hour. Okay. Oh, that's half a day. Okay, that was half a day. 1 divided by 48. Okay. And there's the 318.74. Okay, that's what you want. Okay. Now, notice that's what I got here if I just use 2.505. So if I just hadn't rounded this as much, I would have been all right. So I just make this 2.505. That makes that 05 makes a big difference. All right. So that's B. So that's that. All right. Let's stop this.